So these last four examples that we're going to look at in section 2.3 are combinations of rules, and these are the hardest because oftentimes we're going to have to combine product and quotient rule or product and chain rule or the quotient and the chain rule. So these can be really tricky at first. So if we take a look at our first example, x times the sine of 2x, I need to recognize that first, kind of the outer structure of what we're taking the derivative of is a product, that we have x times the sine of 2x. So I know I'm going to have to use the product rule. But when I look at the two pieces that I'm using the product rule on, I'm also going to notice that the sine of 2x is a composition, because it's not just the sine of x, but it's the sine of 2x. So we have to use the chain rule inside of the product rule. We have to just think of these simultaneously. All right, so if I'm going to take my derivative, I'm going to start with my product rule. My outer structure of this function is a product. And so we're going to take the derivative of the first thing, so the derivative of x, which is 1, times our second thing, our second factor, and that's just the sine of 2x. Then we're going to add to that the derivative of our second factor. So the derivative of the sine of 2x, this is the piece where now we have to use the chain rule because it's not just the sine of x. So I'm going to get the cosine of 2x times 2. So again, that's just the derivative of the sine of 2x. And then I'm going to multiply that with my factor x. So if I go back to how we saw our product rule written, if I think of this as like f times g, this is f prime times g plus g prime, like all of that is g prime times f. And so it's when we're taking the derivative of g, that's when we have to use our chain rule there because that's our composition. All right, so if we were to clean this up a little bit, I would just have the sine of 2x plus 2x, plus 2x times the cosine of 2x. All right, that was another announcement about moving our cars so the band can practice. All right, let's look at the next example at the top right of page 19. So we have, again, we're taking the derivative. We have x times the square root of x squared minus 3. And again, it's really going to help me to, anytime we have a radical, to rewrite that as a power, because we don't have a rule for taking the derivative of a radical. We do have a rule for taking the derivative of a power. So I'm going to write that to the 1/2 power. All right, so similar to last time, structurally, we have a product. We have two things being multiplied, x times the square root of x squared minus 3. But when I get to that second piece, that second factor, the square root of x squared minus 3, that is a composition, right? Like that is some junk to the 1/2 power, and that junk isn't just x. That's a composition of x to the 1/2 power composed of x squared minus 3. So again, we have to use our product rule, and within the product rule, we're going to have to use the chain rule. Okay, so when we go to take our derivative, again, our derivative of x is just 1, and we're going to multiply that with our second factor, our second thing, so x squared minus 3. Factor is probably a better word than thing, but you know what I mean. All right, we're going to add to that the derivative of our second factor, so the derivative of this junk to the 1/2 power. So again, this is where we have to use the chain rule because this piece is a composition. So I'm going to pull out my exponent and multiply with the coefficient of 1 out front. I'm going to keep the junk, the inside function. I'm going to subtract 1 from my exponent. Sorry, my hand is making the screen move. So 1/2 minus 1. That gives me the power of negative 1/2. And then it's really important that I don't forget now to multiply by 2x, because 2x is the derivative of x squared minus 3. And then finally, I still need to multiply this with my original function, x. So if I'm thinking of, how the product rule is written, if I think of this as f times g, this was f prime times g, that was our g there, plus g prime, well, all this junk through the 2x is g prime times f. All right, so we said that's our product rule, f prime times g plus g prime times f. So as we go to kind of make this look a little nicer, to condense this, we'll notice that we have two terms because, again, the product rule produces multiple terms. So we have x squared minus 3 to the 1/2 power. And for our second term, we could go ahead and put a few things together. I could multiply the 1/2, the 2x, and the x. So like 2x squared times that 1/2 out front, that's just going to become x squared. And then I could put that all over x squared minus 3 to the positive 1/2 power. So again, we could deal with our negative exponents by making them in the denominator with positive exponents. All right, so now we said we often want to get common denominators. In order to do that, I'm going to delete my equal sign for just a second to write something out to the side. I'm going to need to multiply my first term. So like right now, this is just over a 1, right? But I could multiply the denominator by x squared minus 3 to the 1/2 and the numerator by x squared minus 3 to the 1/2. So that way I can have common denominators. So when I multiply x squared minus 3 to the 1/2 with itself, remember, multiplying two powers of the same base, I add exponents. So I just get x squared minus 3. And then in my numerator, I have plus my other x squared from my second term, and that's all over x squared minus 3 to the 1/2 power. I'm going to go ahead and change that now back to a square root, now that we're done manipulating it. And then finally, I could just combine like terms in my numerator. So 2x squared minus 3 divided by the square root of x squared minus 3. Notice I don't usually change my 1/2 powers back into radicals until the end, because oftentimes, just like what we saw happen right here, often if we're getting a common denominator, we might need to do something with that rational exponent, and sometimes we get rid of having a 1/2 power in the first place. So, all right, so this is how our answer would be written. And I know it's a lot at first to combine these different rules. I want to point out that in this first step, when we first got here, that was the end of the calculus. And it was still hard. That was the product and the chain rule together. But all the rest of this cleanup is just some algebraic cleanup that we need to be comfortable with. All right, so those last two problems we worked with, they involved the chain rule and the product rule, but that was when we had the product rule and the chain rule was inside of it. Notice this bottom left example, the derivative of the tangent of x times e to the x. So this is similar, but it's kind of the opposite. This is a composition with the product rule on the inside, as opposed to a product with a composition on the inside. So if I were to think about it, my composition is that I'm taking the derivative of the tangent of some junk. And since that junk isn't just x, I've got to think, what is that composed with? That junk is the product of x times e to the x. So we just have to be real careful here. So when I start this, I'm starting off using the chain rule because the outer structure of what I'm looking at is a composition of tangent in x times e to the x. So when we go to take our derivative, I know the derivative of the tangent of some junk is secant squared of that junk. So I'm going to start with secant squared of x times e to the x. So that's like our first step in the chain rule. I've taken the derivative of the outermost thing, but I've kept the innermost thing. I've kept that junk intact. But now the chain rule tells me to multiply by the derivative of the junk. So now I need to multiply by the derivative of x times e to the x. And this is where we have to use the product rule. So the derivative of x we know is just 1 times our second factor e to the x, plus the derivative of our second factor e to the x is just e to the x, times our first factor x. So as I go to clean this up, I get secant squared of x times e to the x times e to the x plus x e to the x. And it's very possible that that's how our answer will be written. Oftentimes, we might see this piece first, like we might have e to the x plus x e to the x first, and then multiply that with secant squared x e to the x. Or another thing that is possible is that we might factor out a GCF right there. So it is possible our answer would have e to the x, our GCF factored out. Then I'd be left with 1 plus x, which is the same as x plus 1 in parentheses, times secant squared of x e to the x. So I think these last two lines are most likely how our solution would be written if this were in fact a multiple choice style question. All right, one last example. If we wanted to do something really tedious here, if we really wanted to bypass using the product rule and the chain rule, we could multiply 2x plus 1 3 times, distribute that 3 times, then multiply x minus 3 4 times. We'd still have to multiply that all together. When I say we could do that, just because we could does not mean we should. That is a terrible idea. I'm 100% sure that I'm going to make a mistake if I do that. If you want to show me that you can do that without making a mistake, I'll be so impressed, but I will still think you're wasting your time, so don't worry about it. This is another time where we can use the product and the chain rule in composition. So again, I want to recognize that I have some junk times some junk. And when I say that, the first factor is a composition. My outer function is x cubed, but it's being composed of 2x plus 1. My second factor, I could also think of as a composition. My outer function is x to the fourth, but it's composed of x minus 3. So I want to think about using the chain rule for both of these factors, but I might also point out that the derivative of x minus 3 is just 1, whereas the derivative of 2x plus 1 is not just 1. So sometimes we don't think of the chain rule as much when our derivative as x minus 3 is just 1. Okay, so again, this is a product rule where I have to use the chain rule within the product rule. So as I take my derivative of my first factor, my 3 pops out front. I have 2x plus 1 to the second power. But the chain rule tells me that I haven't completely taken this derivative of this composite function until I multiply by the derivative of 2x plus 1, which is just 2. So that is our derivative of our first factor. And we know the product rule tells us we have to multiply that with our second factor, so x minus 3 to the fourth. Then we're going to add to that the derivative of our second factor. So the 4 pops out. That becomes x minus 3 to the third power. And again, being mindful of the chain rule, when I multiply by the derivative of x minus 3, I do just get a 1 there. And then again, we're going to multiply this with our original factor of 2x plus 1 cubed. So again, if I'm following the product rule where this whole thing was f and this whole piece was g to start with, my f prime goes from here to here, and this piece is just my g, plus my g prime times my f. So structurally, we could see that's the product rule, but finding f prime and g prime within the product rule, we needed the chain rule. All right, so when we go to clean that up, oh, thank goodness, we don't have any negative exponents. That's wonderful news. I don't know what's going on my computer here. What we might want to consider, though, is if we have a greatest common factor. So it's up to you. Sometimes I like to multiply this 3 and 2 first. We can do that. I think we might end up factoring that 2 right back out, but that's okay. So I could multiply that and say that's 6. Just cleans it up a little bit. I have 2 factors of 2x plus 1, and I have 4 factors of x minus 3. So when I say I have 4 factors of x minus 3, that means x minus 3 to the 4th power. For my second term, we just have a 4 times a 1. We have, I'm going to write these in the same order. So I'm going to say that I have 3 factors of 2x plus 1. And we have, wait a minute, are those both 3's? Yeah, we have 3 factors of 2x plus 1, and we have 3 factors of x minus 3. So now what we'll commonly see is that we'll often pull out a greatest common factor. So if I consider just my 6 and my 4, what's the GCF of 6 and 4? Well, that's just the number 2. In fact, I'm going to do my GCF in orange. All right, next I have to look at my factors of, let's say, 2x plus 1. And each term has multiple factors of 2x plus 1. So I can only pull out from my GCF the least amount of factors that are common to both terms. So that's going to be 2x plus 1 squared. And then finally, both of my terms have multiple factors of x minus 3. So since my right-hand term has only 3 factors, and that's less than the 4 factors on the left, I could only factor out 3 factors of x minus 3 as my GCF. So that's all my greatest common factor. Now, when I go back and I look at both terms, 6 divided by 2, I still have a 3. I divided out all my factors of 2x plus 1, but I still have 1 factor of x minus 3. In my second term, 4 divided by the 2, I still have a 2 there. I still have 1 factor of 2x plus 1, but I divided out all of my factors of x minus 3. So again, everything in orange in that line is my GCF. Everything in purple is what remained from those factors. The last thing we can really do here is distribute and combine like terms if we can. So our final answer, or the way we would expect to see this written, I should say, is we would have 2 times 2x plus 1 to the second power times x minus 3 to the third power. When I distribute within here, I get a 3x minus 9 plus a 4x plus 2. And then I could combine my like terms a little bit more. So I'm keeping my GCF. When I combine these like terms, I get 7x minus 7. Oh man, there's one last thing we could do here. From 7x minus 7, we could pull out a GCF of 7. So that 7 can pop out and multiply with the 2. So the way we are most likely to see an answer to a derivative like this on an AP style test is fully factored like this. And y'all, I know that's a lot of work, but remember, we were done with our calculus step in that very first line. As soon as we did the product rule using the chain rule, we were done. The rest of this is just this algebraic cleanup that's really necessary so that we may find our answer on a multiple choice style test.